how do you figure out what the equilibrium constant is? There's more than one way. The most direct way, although not the simplest way, is just to measure the concentrations of the reactants and products at equilibrium. It's easy to say that, it's challenging to do. So here, they did it, and they found that H2 was 0.11 molar, I2 was 0.11 molar, and high was 0.78 molar. It says calculate Kc. You should always write the expression first before you throw in numbers. So this is going to be high squared divided by H2 and I2. No solids or liquids in here. So what we're really doing here is we're putting in 0.11 molar over 1 molar as the concentration of high. And H2 is 0.11 molar over 1 molar. But I did that wrong, didn't I? This high is 78. This is 7.8. And then this, the I2, both of these guys were 0.11 molar. This is what we are really doing. Do we need to write the per 1 molar all the time? No. We can just understand, oh, that's what we were doing, and all of so the units cancel out. So we don't write the over 1 molar. We just say, oh, yeah, we're not going to put units in the equilibrium constant. But it's not that we just threw them out the window. There's actually a reason. Okay? So we can calculate this. .78 squared divided by 0.1 times 0.1. And I get 50.28 and a bunch more digits. 2 would be a good number of sigfits because that's what the concentrations had. So 50, no units. You need to be careful with your calculator here because this is a mistake I see a lot. Well, let's not do that. Students will do 0.78 divided by 0.11 times 0.11. Does that give you 50? It does not. It gives you 0.78. Because your calculator understands that to mean 0.78 divided by 0.11 times 0.11. Not the same. So, 2 ways that are popular with students to avoid this problem. One is parentheses. Use parentheses. Do not use parentheses around every single number. Then they become meaningless, right? Only use them if you need them. The other thing you can do is use the box over box button on the calculator. And then you can type it in just the way it looks. You don't have to worry about that. Personally, what I do is I do this divided by that, divided by that. But that confuses students, so I won't talk about that anymore. Because we didn't have box over box or parentheses when I was learning this stuff. We had parentheses, but not in the calculator. Yeah.
Is the reason why it's Kc because there is an overall change in concentration?
Pardon me?
Is the reason why it's Kc because there's a change in concentration?
The reason that it's Kc is because they reported the amounts in moles per liter. They reported the concentrations. If they gave us partial pressures, then we could calculate KP.
Okay.
Yeah.
So if we saw ATM, like one more than ATM,
Mm-hmm.
then it would be,
KP.
oh, that is.
Yeah. But then sometimes it might give you pressures and ask you for KC. So what do? Well, you use a little equation with the RT to the delta M. Remember that guy? This guy. So KP is equal to KC times RT to the delta N. So just for fun, it's no fun though, because what's delta N? 0. It's the same number. If you're using molarities, you're calculating KC. If you're using atmospheres, you're calculating KP. Occasionally they're the same, most often not. Any questions? Now I have to go back to where I was. Okay, so let's look at this. This is that same reaction. And so here, they've started with different initial concentrations, and they've done an experiment. So when they started with 0.5 and 0.5 of reactants and no product, they ended up with this. That's the one we just calculated. It came out to be 50. If we start with none of the reactants and 0.5 moles per liter of the products, we end up with these concentrations. How do we know what those concentrations are? Somebody measured them. Well, you plug those numbers in and you get 50 again. It doesn't matter what you started with. When it gets to equilibrium, the equilibrium constant is always the same, provided you didn't change the temperature. So this equilibrium constant being 50 doesn't tell us what these numbers are, but it gives us information about the relationship of them. That make sense? We can also calculate K if we know the initial concentrations of the reactants and one of the equilibrium concentrations. This is, practically speaking, much easier because when you do a reaction, you have control over what concentrations you put in. It's like, well, I'm going to put in the reactants, and I'm not putting in any product because the point of the reaction is to make the product. I don't have any, right? That's why I'm doing it. And then you measure one thing. It could be the product. It could be one of the reactants. Doesn't matter. You just measure one thing. And so to do a problem like this, we end up deducing the concentrations using stoichiometry. So here, the reaction we're looking at is A is in equilibrium with 2B. So we're going to have an initial row. This is the initial concentration of A. The initial concentration of B, the product, was 0. At equilibrium, somebody measured it and found that the concentration of A was 0.75. This is all the information we need to calculate K. How do we do that? So A started at 1. We had 1 molar of this and none of that. So the reaction is going to go in the forward direction to get to equilibrium. You can't go backwards because there wasn't any B. So we're going to lose some of this, right? Let's call that X. So the A concentration is going to go down by X. And the B concentration is going to go up. But for every 1 mole of this, I make 2 moles of that. So it goes up by 2X. Now I can look at the column where I do have an equilibrium concentration. And that is telling me that 1.00 minus x is equal to 0.75. So x must equal 0.25. So over here, we're gaining 2 times x. So this is plus 2 times 0.25. So this is going to be 0.5. We're going to be using tables like this for 3 different chapters. We refer to these as ICE tables, ICE. Initial, change, equilibrium. Are you guys too young to know about ICE, ICE, baby? Okay. It just always goes through my head. ICE, ICE, baby. Anyway, ICE tables. So what we're putting the initial concentrations, then we're looking at the change. We're going to use X and the coefficients of the balanced chemical equation. This one had a coefficient of 1, so it's minus 1x. This one's plus 2x because of the 2. Okay? And then we know one of these, so we can figure out what x is, and then we can figure out what this one is. So, how would we calculate the equilibrium constant? Well, Kc is going to equal the concentration of B at equilibrium squared over the concentration of A. Concentration of B is 0.5. That's going to be squared. Divided by A, 0.75. 0.333 repeating, just keep 2 sig figs. Any questions? So here we did it with A's and B's. Let's do it with actual chemicals. So here we have a reaction between carbon monoxide and hydrogen, and it's making methanol. And it says it's carried out with initial concentration. Carbon monoxide is 0.27, hydrogen is 0.49. What's the initial concentration of the CH3OH? They didn't say. If they don't tell you anything about the product, we should assume that it's 0. Sometimes they'll tell you, oh, well, it started out with this much product and these reactants, and they'll give you numbers for everything. But most of the time, not. We need an ICE table. So I'm just going to use the chemical equation here for the top of my ICE table. So this is my header row, and this is going to be initial and change and equilibrium. So I need separate columns for each of these. This is where I lose everything. This is where the equal sign is. If I make a line like this, I find that I sometimes forget where the arrow is. So what I like to do is put a double line here to help me remember, okay, these guys are on one side, that guy's on the other side. This is not anything in the book or anything, this is just what I do. Okay, there's our ICE table. We're going to use the information and put it in the table. So carbon monoxide, 0.27 molar. That's the initial concentration. Initial concentration of hydrogen, 0.49. So we put that in here, 0.49. Initial concentration of the product, 0. And then they give us the equilibrium concentration of this product, 0.11. So I'm going to put that in there. Okay. ICE table, you got ICE, initial change equilibrium. These types of problems, they're going to give you some initial concentrations. They'll give you one equilibrium concentration. And use the reactants and products as the tops of the columns. Okay? Now we need to figure out what the change is. Well, we started with no products. This reaction can only go in the forward direction. So this has to go down. So it's going to go down by x. What's the coefficient on this? 1. So this is 1x. This one's going to go down by 2x. And how's the product going to change? Plus 1x, just plus x. Okay? So you'll have one column where you know all the numbers. And so you can think of this like you're adding. Oops. That's not very fast. That's my addition line. I'm taking this plus this equals this. This plus this equals that. Well, I have to figure out what x is. 0 plus x is 0.11, so x must be 0.11. So that means over here, and I'm just going to kind of sneak it in there, this is minus 0.11. So 0.27 minus 0.11 is going to be 0.16. This one's minus 2x, so minus 2 times 0.11. So 0.49, turn on the calculator, 0.49 minus 0.22, 0.27. We write our equilibrium expression, products over reactants, CH3OH divided by CO and H2 squared. And then we plug those numbers in. So 0.11 divided by 0.16 times 0.27 squared. .4. Any questions? We're going to be using the ICE tables to do some kind of difficult things later. At this point, it's very straightforward and simple. And so I want to make sure that everybody really understands what we're doing here. Because it's not hard, right? We're just taking the stoichiometry and we're adding and subtracting moles. But, you know, you might just have a little glitch in your brain that it's not making sense to you. And today's the day to ask me questions about that so that we can get that straightened out. Because if you understand how this works, it makes the rest of it much, much easier. So next, we're going to do this one. And I want you to get started on that one by yourself. made the ice table. Initial concentration, CH4 is 0.087. 0.087. That's all they tell me. I am supposed to assume then that there's none of the others. If there was some, they'd have to tell me what it was. So I get numbers in for the I row, and then for the E row, they're going to tell me one of them. So they're telling me that H2 is 0.012. So I'm going to write that in here. We can think of this as a table where we're taking the initial and adding the change to get the equilibrium. So we're going to use X to show what's happening here. The reactant is going to go down in concentration. That goes down, minus X. And because there's a 2 here, I'm going to put a 2 in front of the X. The products are going up. What would I write for the C2H2? Plus X. And for the H2? Plus. So here I'm adding X. X is 0.004. So 0 plus 0.004 is 0.004. 0.087 minus 2X. You can write it out, or you can just type it into your calculator. 0.087 minus 2 times 0.004. 0.079. Any questions? Write the equilibrium expression. Products, C2H2, H2 to the third power, because it has a coefficient of 3, divided by CH4 to the second power. Some of you may be tempted to say, well, I don't need to actually make the ice table. I can just figure it out in my head. Make the ice table. Just make the ice table. This stuff's pretty simple. We're going to get to some stuff where you really do need to write it down. So we need to learn how to write it down. And then always write down the expression here. This is, I know you probably got pounded with, show your work, in elementary school and high school and stuff, right? You're like, but I did it in my head. I have one of my kids that just, he's got like a computer for a brain, and he can't even necessarily tell you how he did this algebra. He just like sees it. And so that's a hard thing for him. But in science, we need to be able to explain to somebody else what we did. It also helps us if we make a little mistake along the way. We can go back and check our work instead of doing the whole problem over again. We can go back and look at it and find the mistake, or you're stuck on something at home, you send me a picture of what you're doing, I can look at it and, oh, this is the problem. So you should always write this out, and then you should write it out with the numbers plugged in. This is 0.012 cubed, 0.079 squared. Do I want to see you rearrange and write out algebra and stuff? No, I don't want to see it. If you want to write it, that's fine. But from here, you can go to the answer, okay? So 0.004 times 0.012 to the third power divided by 0.079 squared. My calculator is giving me this. 1, 2, 3, 4. I don't have dyslexia that I know of or any issues of that sort. But when I look at that, those zeros kind of swim. I can't count them reliably. I know there's 5 because I used my Apple Pencil and I tapped 1, 2, 3, 4, like a kindergartner pointing with your finger and counting, right? So kind of my rule of thumb is if there's more than 3 zeros at the front, scientific notation is best. 3 zeros we can see. 1, 2, or 3. After that, not so good. That's what my calculator's giving me. If you're curious and don't know yet, there's a way to make your calculator show this to you in scientific notation, or we can just convert it. I'm going to use 2 sig figs here, so I'm going to 1.1. 1, 2, 3, 4, 5, 6 times 10 to the 6. Positive 6 or negative 6? Negative 6. Because that's a small number. If that was my paycheck, I'd be very negative. Right? Any questions? Yeah. That's a great question. What determines whether these are positive or negative? Well, in the cases that we've looked at so far, we've started with reactants and we've had no products. So can we go lower than 0? No, we can't. If we put negative x here and negative 3x and put plus 2x here, it's important that the negatives are on one side of the arrow and the positives are the other. You can't just sprinkle them around. If you got the signs wrong, what would happen is that x would be negative 0.004. And you can plug that in and you'll still get the right answer. Yeah. Any other questions?